Good day and welcome to Big Bad Tech. I'm instructor Jim Pytel, and today's topic of discussion is logarithms and decibels. Our objective is to take a quick look at logarithms and logarithmic properties on a very basic introductory level. Additionally, we'll examine the concept of gain expressed in units of decibels. Later lectures will make use of logarithms and decibels to plot the performance of electrical circuits. This is a lecture for people that dislike logarithms, written, recorded, edited, and published by a person that also dislikes logarithms. Trust me, I've been there. As a first-year basic electronics student, way back when the wild mullet still cruised the earth, I distinctly recall thinking, as if basic electronics wasn't hard enough, they throw in a dubiously necessary level of mathematical complexity to make it that much harder. Ultimately, I learned logarithms because I had to. However, after gaining a little familiarity with logarithms, I grudgingly admitted they did serve a purpose. It didn't mean I liked them, but I did understand why they're used. My hope is that this lecture will provide you the tools necessary to get past this obstacle with a minimum of tears, sweat, and toil. You don't have to like logarithms, but you do have to coexist with them. Let us begin. You are no doubt familiar with exponentiation, where a base b is raised to a certain power x to yield a specific number n. Consider the expression 10 raised to the 2, which is 10 times 10, which yields 100. Similarly, consider 10 raised to the 5th power, which is 10 times 10 times 10 times 10 times 10, which yields 100,000. Exponentiation needn't be restricted to a base of 10. Consider the expression 2 raised to the 3rd power, which is 2 times 2 times 2, which yields 8. Nor is exponentiation limited to rational numbers. Consider the expression e to the 2nd power, which is e times e, or roughly 2.72 times roughly 2.72, which yields roughly 7.39. By now, you should have had plenty of experience with exponentiation. A logarithm, if you want to think of it this way, is exponentiation in reverse. It answers the question, to what power do you have to raise a base to get a specific number? The logarithm operation is written log with a subscript to the base b and the number n in parentheses, which yields the power x. Consider the expression, to what power do I have to raise 10 to get 100? Written as log base 10 of 100. The answer is quite obviously 2, since 10 raised to the 2nd power equals 100. Similarly, consider the expression log base 10 of 100,000. The answer is 5, since 10 to the 5th power equals 100,000. Similarly, log base 2 of 8 is 3, meaning 2 must be raised to the 3rd power to get 8. Finally, log base e of 7.39 is 2, meaning e must be raised to the 2nd power to get 7.39. A log lacking a base subscript means the base is assumed to be 10. This is sometimes referred to as the common log, since people commonly think in powers of 10. We could just as easily rewrite the first two examples as log 100 equals 2 and log 100,000 equals 5. Log base e also gets its own special notation as ln, which stands for logarithmus naturalis, or natural log. We could just as easily rewrite the last example as natural log of 7.39 equals 2. You'll recall we used the natural log function when we examined the transient charge and discharge process for capacitors and the transient storage and release process for inductors. Today's lecture deals with the common log only, where the common log again always utilizes the assumed base of 10. Way back in the days of the wild mullet, you had to look up the common log of a number in huge tables written in small print, but nowadays scientific calculators make the job easy. To perform the common log function on the Texas Instruments TI-89 Titanium Edition Scientific Graphing Calculator, one can look up the log function in the catalog, or simply press the light green diamond key followed by a 7 for a shortcut. The calculator says log, followed by an open parentheses. Let's say we want the common log of 100,000, which is asking the question, to which power do I need to raise the assumed base 10 to get the number 100,000? Diamond 7, enter 100,000, close the parentheses and hit enter. The calculator spits back the number 5, as you might expect. Let's try something harder. Consider the expression log of 40, meaning to which power do we need to raise the assumed base 10 to get 40? Diamond 7, enter 40, close the parentheses and press enter. The calculator spits back the number 1.6. Let's check our work. 10 raised to the power of 1.6 is indeed 40. Oh my gosh, it works. Your turn. Try these example problems on for size. Log of 90, log of 2,400, and log of 8. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. You'll note that the number 8 being less than the base of 10 necessitates 10 be raised to a power of less than 1, in this case 0.9. This makes sense. Let's look at some other weird properties of logarithms. Try this one on for size. What's the log of 1? The calculator says 0, which again makes sense. Anything raised to the 0 power, in this case the base 10, raised to the 0 power is 1. What about the common log of positive numbers smaller than 1? Consider the expression log of 0.1. 10 raised to the negative 1 is 1 over 10 raised to the 1, or 1/10, where 1/10 in decimal form is 0.1. What about log of 0, or log of a negative number? It don't work, so don't try it. Log functions only work for numbers greater than 0. We're left with a couple important observations about the common log function. Common log functions only work for positive numbers greater than 0. Logs of positive numbers smaller than 1 are negative. Log of 1 is 0. Logs of numbers between 1 and 10 are always less than 1. Log of 10 is 1. And finally, logs of numbers greater than 10 are always greater than 1. If you get answers that violate these rules, you are doing it wrong. The visual thinkers among you may wish to incorporate a plot of the common log function in their cheat sheet summarizing these guidelines. Here's some other helpful properties of logarithms. Log of a times b will be equal to the log of a plus the log of b. Log of a over b will be equal to the log of a minus the log of b. And finally, the log of a raised to the power n will be equal to n times the log of a. Let's do a quick application of these properties by way of illustrated examples. Consider the expression log of 12 times 50. We could multiply the numbers inside the parentheses to yield log 600, which yields roughly 2.78. Or we could take the log of 12 and add it to the log of 50. Log of 12 is 1.08. Log of 50 is roughly 1.7. 1.08 plus 1.7 is 2.78, as we anticipated. Similarly, consider the expression of log of 2,400 over 30. We could divide the numbers inside the parentheses to yield log of 80, which yields roughly 1.9. Or we could take the log of 30 and subtract it from the log of 2,400. Log of 2,400 is roughly 3.38. Log of 30 is roughly 1.48. 3.38 minus 1.48 is 1.9, as we anticipated. Finally, consider the expression log of 16 raised to the 4th power. We could perform the operation inside the parentheses to yield log of 65,536, which yields roughly 4.8. Or we could take the log of 16 and multiply it times 4. Log of 16 is roughly 1.2. 4 times 1.2 is 4.8, as we anticipated. Now that we've got an understanding of basic logarithms and basic logarithmic properties, let's answer an important question. Why is this useful? There's a couple of reasons why logarithms are employed in electrical circuit analysis. The first and most important reason being that it makes circuit analysis seem that much more arcane and mysterious than it really is. By obscuring straightforward analysis with a dubiously necessary level of mathematical complexity, it ensures generations of electrical engineering technicians continue to make top dollar. Second, logarithms make it possible to plot the response of a system for a wide range of values that would be unmanageable or impossible if done so using a linear scale. Third, similar to engineering notation, logarithms make it possible to quickly compare extremely large and extremely small numbers with one another. 4. Many systems and properties exhibit nonlinear response to a stimuli. As we learned in the transient analysis of capacitors and inductors, these devices exhibit nonlinear natural logarithmic decay and rise functions. And finally, 5. Using the previously demonstrated properties of logarithms, it's possible to quickly determine the output of a cascaded series of systems, where one system's output is another system's input, and so on. First, allow me to demonstrate the utility of plotting numbers using logarithms. If I was to plot the response of a system over a broad range of frequencies, let's say from 0 Hz up to 1 MHz, using a linear horizontal scale, where numbers employ evenly spaced intervals on the horizontal axis, the graph would be unwieldy and almost impossible to use. If I started on the left-hand side and said every 1 inch means 1,000 Hz, I'd quickly run out of room on my screen. Using a linear scale means a graph from 0 to 1 MHz will be 1,000 inches wide. Even if we use paper in landscape orientation, this would take 87 pages of 8.5 by 11 notebook paper. If I was to draw a graph this big, it'd stretch from my office in the Dalles, Oregon, down the hill, through downtown, across the Columbia River, and into Murdock, Washington, where it'd probably get stabbed in the back with a broken wine bottle by the dirty, paint-huffing subhumans that seem to populate Murdoch. This is obviously not a workable solution. If, however, we use the semi-log plot, where the vertical y property, whatever it might be, is still represented linearly, and the horizontal x property, in this case frequency, is now represented logarithmically, it's possible to squeeze everything inside one nice neat chart and fit it on one page. The linear vertical y scale plots some property of interest, either voltage, current, or power in a traditional linear sense. However, the logarithmic horizontal x scale starts at 1 and spaces each power of 10 evenly. In this case, a power of 10 every 1 inch. 1 to 10 hertz is 1 inch, 10 to 100 hertz is 1 inch, 100 to 1000 hertz is 1 inch, and so on. The upper end of our horizontal scale, in this case 1 megahertz, is now only 6 inches away, making it possible to fit the chart on one page, leaving us with a whole bunch of unused pages in our notebook to start random fires with around the campus. Let's take a look at some semi-log paper. In a semi-log plot, you will note the compressed right side of the logarithmically scaled horizontal axis. Inside each equally spaced power of 10, you'll note a repetitive pattern. Consider the span from 1 to 10 hertz. At roughly 30%, we're at 2. At roughly 48%, we're at 3. At roughly 60% across, we're at 4. At roughly 70% across, we're at 5. At roughly 78% across, we're at 6. At roughly 85% across, we're at 7. At roughly 90% across, we're at 8. At roughly 95% across, we're at 9. And finally, at 100% across, we're at the next power of 10, in this case, 10. You may wish to take note of these percentages and numbers because they repeat themselves inside every power of 10. Consider a point, let's say 60% of the way between 1000 and 10,000 hertz. This means we're at roughly 4 times 1000 hertz, or 4 kilohertz. Consider a point, let's say 85% of the way between 100 hertz and 1000 hertz. This means we're at roughly 7 times 100, or 700 hertz. Coming at this from a different direction, let's say we wish to identify where exactly 200,000 hertz, or 200 kilohertz, appeared on this chart. 200 kilohertz is between 100 kilohertz and the next highest power of 10, in this case the top of our scale at 1 megahertz. 200 kilohertz is 2 times 100 kilohertz. This means we'd be roughly 30% of the way between 100 kilohertz and 1 megahertz. Is interpreting numbers on semi-log plots easy? No, it's not. Does it require practice? Yes, it does. That's the purpose of the hardware lab I drag you through each week. Believe me, you'll get more than enough practice. Is all this practice worth it? Yes it is. Look at what we just did. We can plot an entire 1 megahertz range on a single graph and fit it on a screen. In summary, logarithms make it possible to cram lots of information into a very small space.